Welcome everyone. Thank you for joining LRVS Lubrication and Reliability Virtual Summit 2020. Uh, and we are happy to introduce to you Manas Ranjan Pattnayak, PhD Research Scholar, Indian Institute of Technology in Delhi. He will be talking about very interesting topic, and he will be sharing with us the information about air lubrication for the environment and sustainable development of industrialized humankind, present and future prospect. Welcome, Manas.
Hello everyone. May I confirm if I'm audible or not?
Yes, you are. You are.
All right. So, hello everyone. Today my presentation topic is air lubrication for the environment and sustainable development of industrialized humankind, its present and future prospects. A brief introduction about me. I am currently a full-time PhD research scholar in the Department of Mechanical Engineering at the Indian Institute of Technology, Delhi since July 2018. I have obtained my bachelor's degree in 2018 June from National Institute of Technology, Rourkela, India. I am a recipient of the country's prestigious Prime Minister's Research Fellowship Program. My primary research interests are aerodynamic lubrication, gas foil bearings, oil journal bearings, modeling of different lubrication regimes, rotordynamics, vibrations, numerical methods, and machine design. The topic of the presentation will consist of these outlines. First, I'll start with the background, following which the introduction and classifications of various air lubrication technologies, its different working mechanisms, various limitations and what are the ongoing research in this field, the scope of research for future. So coming to the background, in the area of turbo machinery, the oil lubricated journal bearings and rolling element bearings have been primarily used. However, these oil lubricated journal bearing supported rotors have various disadvantages, such as use of oil as lubricants, which are not environmental friendly, design of supply and storage systems for lubricants, deterioration of lubricant viscosity at elevated temperature, leading to loss of load carrying capacity, corrosion of process equipment due to direct contact with the lubricant, very high friction in the order of 10 to the power minus 4 to 10 to the power minus 3. Similarly, for the case of a turbo machinery of rotors supported on rolling element bearings, there are multiple disadvantages such as low damping, noisy operation, low resistance to shock loading, high weight, high friction in the order of 10 to the power minus 3. Again, use of grease or oil as lubricants, thermal distortion at elevated temperatures. So these turbo machinery supported on conventional oil lubricated and rolling element bearings have limited speed applications due to the certain disadvantages. However, the modern turbo machinery demands ultra high rotational speed operating from cryogenic to severe operating temperature environment in order to enhance the operational efficiency. So this gives the motivation to work on and develop a green technology. So what is the proposed solution? Air or gas lubricated bearings for use in modern turbo machinery. Coming to the advantages of air and gas bearings, these bearings do not use any oil or grease. Hence, the environment is oil or grease free. Hence, it is a green technology. Very low coefficient of friction in the order of 10 to the power minus 4. Sometimes it can go to 10 to the power minus 6 as well. Operation from cryogenic temperature to extremely hot temperature, reduced weight, and maintenance due to elimination of all supply and storage systems. So here I have shown two different kinds of air bearings. First is the aerodynamic bearings, which do not use any external supply. The design is very simple. It is just a hole under which the rotor will be supported. The second type of air bearings are the aerostatic bearings, where we will be supplying externally pressurized air to lift the rotor. So the few applications of these air or gas bearings are like air cycle machines to maintain the atmosphere and temperature inside the commercial and fighter aircrafts, turboprops used during the launching of space launch vehicles, cryogenic turbo expanders to liquefy nitrogen or many other gases, high-speed automobile turbochargers, medical centrifuges, dental handpiece, miniature gas turbine engines and fuel cells, spindles of textile and food processing industries, coordinate measuring machines. So all these applications can be classified into two types. First, high-speed micro-turbo machinery where aerodynamic bearings are primarily used. The second, high-precision instruments where aerostatic bearings are primarily used. Coming to the introduction, how the air bearing looks like. So here it can be seen that there is a bearing sleeve and there is a rotor, and inside which the air or gas is there. So the rotor is floating over a thin film of air or gas, as like oil lubricated bearings where a thin film of oil is there. Here, in place of oil, air film is there. So the requirement of fluid pressure generation between two bodies are there has to be a convergence wedge to generate the pressure. There should be relative motion between the two bodies. So when the rotor will rotate, then only the pressure will develop. The third point is the finite viscosity of lubricant, which the air has. However, the other type of bearings as the aerostatic bearings, which uses external pressurization. The working mechanism: when the rotor rotates in the converging zone, there is a development of aerodynamic pressure. However, in the divergent zone, where the film thickness gradually increases, there is the creation of suction. So the atmospheric air sucks inside the bearing in this region, and the same air gets circulated in the converging region to develop the aerodynamic pressure. Here, this is a representation of the variation of film thickness and the pressure. So clearly, there is two distinct regions in the air bearings. The first is the positive pressure zone, and the second is the negative pressure zone. So this is also have been verified by experiments. So here it can be seen that this is basically the bearing. The rotor is connected to the motor using a belt drive. The rotor is rotated, and at the same time the pressure is developed inside the bearing. So the same pressure can be seen in the manometric tubes. So here it can be seen that for certain regions there is positive pressure, and in this other region there are negative pressure or vacuum. So in the vacuum region there is a suction of air, and the same air will get circulated in the positive pressure zone. So this is the schematic and experimental and computational validation of the two pressure profiles. However, these air bearings have couple of limitations. First, low load carrying capacity due to extremely low viscosity of air compared to oil. The second, fluid induced dynamic instability, such as subsynchronous vibrations, nonlinear and chaotic vibrations, pneumatic hammer, which is generally seen for aerostatic bearings. The third limitation is the direct metallic contact during the startup and shutdown when there is not enough gas fill. These all limitations have major reliability issues for the gas air bearings. So, as I mentioned, the subsynchronous vibrations, the vibrations. However, the rotor supported on air bearing show severe subsynchronous vibrations. So these are the example of the synchronous vibrations. The second, chaotic behavior. This is the observance of chaos in rotors supported on air bearings, which is not desirable. Therefore, what are the ongoing research to eliminate these disadvantages? The primary research is based on both geometry modification techniques incorporating pockets, textures, grooves, or lobes. So here it can be seen that there are varieties of bearings where on the rotor there are varieties of textures like grooves. Here you can see there is a helical groove, this is a herringbone groove. Here the bore is elliptic bore, this is a conical bore. There are different textures present on the bore. Similarly, there is a pocket or textures. So all these yield performance improvement in air bearings. The same thing has been shown here. Here we can see on the bore we have introduced pockets, and after the pocket there are textures. So these new bearing bores improve the performance of air bearings. So why these textures or pockets improve the performance in air bearings? So what we observed in our research is that these tiny dimples acts as micro reservoirs which stores gas or air film and provides lubricity to the interface. The second, these small dimples act as micro small bearings. So there is a larger bearing as well as there is small micro bearings which induces pressure spikes to improve the load carrying capacity. The third improvement is the third mechanism is even if certain debris gets generated, these dimples can trap these debris and restrict the damage of rotor and bearings. The second ongoing research is the use of compliant bore. So here it can be seen that the figure A is a rigid bore, the second B is a tilting pad air bearings, and the figure C, D, and E are compliant bores where the bore itself deforms as a result of aerodynamic pressure, due to which it enhances the dynamic performance of rotors supported on air bearings. A lot of bearings have been developed by varieties of researchers. So all this summary of all the bearings can be held in a review paper, which is recently published, an overview and assessment on aerodynamic general bearings with important findings and scope for explorations. So here, researchers have used metal meshes, flexure pivots, two different lower bumps, upper bumps, a combination of slips and foils, and there are varieties of mechanisms by which different compliant bore bearings have been developed by the researchers. However, the design principle of such air bearings are still not standardized or are still not unique. So, based on the customer's requirement, there is a customized design of various air bearings. So, what are the overall design principles of an air bearing? So, design should be for maximum load carrying capacity, maximum power loss, minimum rotor runout. What are the design parameters? Bearing clearance, bearing diameter, bearing aspect ratio. What are the operating parameters? Applied load, rotational speed, temperature, humidity, etc. And the constraints are manufacturing precision, cost of air bearing parts, manpower. So there are varieties of passive methods and active methods to improve the tribological and dynamic performance as well as thermal performance. So the certain examples are using textures, pockets, or groups by tailoring compliant bore geometry to vary stiffness of compliant bore, use of extra structures such as viscoelastic foils, external dampers, use of safe memory alloy springs under the top foil to control the bore stiffness, use of active electronic sensors, use of magnetorheology waste fluid, use of solid lubricants to minimize the heating during the rotor start and stop. Again, using surface textures to efficiently dissipate the heat, modification of housing and bore geometry to aid in effective removal of heat from the system. Similarly, some active methods to improve thermal performance include in situ measurement of temperature of AJV components and supply of cooling air, use of thermoelectric modules, mini fans to actively control the temperature, use of active coolant flow systems under the bore top five. A new direction of research has recently been published in Tribology International, where our proposal was that we observed that the rotors supported on air bearings accelerate to or deaccelerate from their operating speed quite a sometimes during their operation. So what if the rotor will fail during the acceleration or during the retardation? So we proposed a new research where we established the rotordynamic behavior of accelerating rotors supported on aerodynamic journal bearings. In this article, we have also proposed a type of control algorithm to control the rotordynamic response during the acceleration and retardation to minimize the vibrations and frequency of oscillations. What are the scope of research for future? The first point is the exploration of operation of rotor air bearing system in the mixed lubrication region, where the surface apparatus interact with each other in addition to the air lubrication. So here it can be seen that for a case of journal bearings or for a case of slider bearings, when these bearings will operate in mixed lubrication regime, in addition to the air lubricity, there is also friction due to the asperities. The second research, which is vital, is the fracture and fatigue behavior of rotor supported on air bearings. By this research, we certainly will improve the reliability of air bearings, conducting rigorous long duration rotordynamic tests to explore life and reliability of air bearings. Development of active aerodynamic bearings to alter bore geometry and stiffness distribution according to the need. Standardization of bearing size and preparation of bearing design charts is like oil journal bearings for rapid evaluation of bearing performance. And there are many more research areas which should be done. One interesting fact: unlike liquid lubricants, the viscosity of air or gas increases with rise in temperature, which enhances the load carrying capacity of air bearings. However, with rise in temperature, the rarefaction also rises. This creates an adverse effect on the load carrying capacity of such bearings. Thank you. I welcome now the questions.
Wow, that was interesting. That was really interesting. And I have a question personally. I think you explained it, but I didn't really get it very well. So, when air is lubricating, why the pressure of the air is not equal from all sides?
Okay, first, the thickness. The film thickness between the rotor and your stator is not uniform. So it provides variety difference in pressures.
Sorry, can you repeat it again?
Yeah, the film thickness between the rotor and your stator, that is not uniform, that is not constant, that is that provides a converging wedge or a diverging wedge. So due to that effect, the pressure is not constant inside the air bearings.
Okay. So your study, your paper research, it work on solving this issue, correct?
Sorry.
The paper, the study paper you mentioned, it works on solving this issue of the pressure of the air to be constant.
Yes, the major disadvantage of these air bearings are low load carrying capacity and the rotor supported on them are highly unstable. So focusing on these two aspects, we are conducting our research to improve the load carrying capacity and improve the dynamic performance so that the industries can certainly use this technology and the reliability of such bearings can be increased.
So do you think in the future we'll be able to transform this technology to be used in, for example, power generations, or like
Yes, we are
instead of,
trying that only because this is a green technology. So there is no carbon footprints as like oil bearings or something like that. So if we can completely eliminate the oil systems, that will be great. That will be a very greener technology.
perfect. Thank you so much for your time. Thank you so much for the presentation. Thank
Thank
you for
you.
the audience who participated in the presentation. Also, if you have any question for Manas, you can reach out to him through his email. His contact, I think, will be provided by the moderators, the organizers of the event. So you can reach out for him anytime for any questions. Thank you, Manas, again. It was a
Thank you.
pleasure.
Thank you.
Okay, God bless